Thank you for joining us for our COVID-19 image classification project. I am Matt with Sood, Jay, and Paul. In terms of our motivation, the reason we chose this project was fairly obvious. We wanted to do data science for good. We were all interested in a public health domain, and the obvious part is that we are in a online data science master's program that is inescapable from the COVID-19 pandemic. And so we wanted to study this as a backdrop for our program. We also wanted to really hone a lot of the skills that we learned in this class, and this project presented a unique opportunity to look at image classification and a lot of the individual skills that we practice in this course.
So as soon as we started, we ran into a set of challenges, and even Professor warned us. They say, hey, that you might not get the right data, but we still wanted to do this project. As Matt said, this was an opportunity for us to be applying data science for good, for something that has impacted all of our lives. More so, we wanted to use some of the things we've learned in the semester, which is related to transfer learning, and apply some of these models like ResNet 50, VGG16, MobileNet V2. So we started with the first approach, and in our first approach, our idea was that we'll take these 100,000 images, which is an NIH data set, with 15 classes, and train a model, and use the best model and apply transfer learning onto these smaller data set with 300 images with 3 classes. And what Professor predicted came true, where our accuracy was very low. We constantly ran into issues with overfitting. So we added a second approach, and Jay is going to go more into detail, but essentially the idea was that we take the best trained model from our approach 1 and apply it to yet another data set. So we took a lot of different permutation combination of unfreezing on different layers, and Jay is going to go and talk more into the different experimentations we did with both the approaches. Jay, on to you.
Thanks, Sood. So just to continue from where Sood left, so in our approach 1, we tried to train the model on the larger NIH data set of X-ray images. The step 1 was to get a better trained model and use it in step 2. So as you can see here, as we started experimenting for the step 1, training the models on the larger NIH data set, we struggled to get higher accuracy. Our accuracy was in the range of 0.51 to 0.56 at best in different runs. You're seeing a snapshot of a run here. We saw consistently better and our consistent results from ResNet V2. So we choose that to be the go-to model in our step 2. So the results in our approach 1 for step 1 and approach 2, step 1, were consistent. So this would be sort of same results for approach 2 as well. So let's go to the next slide. Here, I'm mostly presenting the results from the model training and validation on the larger COVID data set. As Sood spoke, in our first approach on the smaller data set, we saw consistently overfitting, right? So as you can see, the first 3 results here, first 3 rows represent the pre-trained model, the best performing ResNet V2 model, trained all layers frozen, unfrozen all layers, and unfrozen at layer 186 and above. So you can see the results are somewhat better than what we saw purely for the approach 1. However, one anomaly here is when we unfroze all the layers, we saw the result, accuracy was going down relative to the other 2 runs. And a tweak to our approach 2, which Sood suggested earlier, is to train the ResNet V2 model directly on the larger COVID data set of 3,000 images. The last 2 results here of 0.871 accuracy and 0.942 accuracy represent that experiment, right? So as you can see, our observation was when we used the backbone model, ResNet v2 model, trained on ImageNet database, and we directly used it on a larger COVID data set, we got consistently better results. In fact, our best result was when we unfroze the model at layer 186 and retrained and validated. We got an accuracy of 0.942. That's 92% training and 87% in validation accuracy. So it did not overfit. We achieved a higher accuracy, and the expected result was also not overfitting. So we achieved both the goals. Let me hand it over to Paul, and he will highlight on what we learned and conclude.
Yeah, so on the right is just an image from one of our runs. It's not necessarily the focus here. It's just that you can kind of see that you're always fighting a number of epochs as you go. You're fighting the training and validation accuracy, and you're trying to see how you're doing and monitoring your progress. Just something to keep in mind. And looking on the left, some of the things that we learned and the takeaways, you don't know what kind of data you're going to be faced with. You could have large data sets, small data sets. You're still going to have to get the job done. And so you're going to have to be creative. You saw and heard Jay talk about a number of different approaches, just really trying to fight to higher performance results, faced with different challenges as we go. We did learn that, as you're trying these different approaches and different experiments, that ResNet 50 was just very adaptable, very flexible. The other models were as well, but ResNet 50 just seemed to be a really useful tool to kind of try different experiments and see how it progresses. And then just lastly, just some takeaways as well on basically the knobs that we learned how to tune as we're going through it, is that sort of the first sub-bullet there, learning rates, epochs, and compute, all of those things go together. And if you have huge compute constraints, you're gonna have to potentially dial down the number of epochs. You can go the other way if you don't have those compute constraints. And your learning rate is one of the larger things that you really have to optimize. You've got to get it right. You might have an issue that we found early on, is that you converge too quickly, and you kind of quit learning early on in your epochs. One of the things we did there is we tried to use early stopping and guard against overfit. We tried to use an adaptive learning rate to get over those early convergence issues. We also found that in terms of overfit, that adding some regularization through dropout was just a really huge beneficial tool. And all of these were made possible by Keras, sort of that last sub bullet. Keras is a powerful tool. There's a lot in there. When it came to data augmentation, using the image generator, basically a couple of different lines, a couple of different arguments, and you're really on your way towards improving the availability of your data for training. And those are some of our large takeaways. This was a fun project. It was a real world example. It put us in, I think, the shoes that any of us could find ourselves in a real world job, and we really enjoyed it. So thank you.